photosphere has enormous energies. For instance, if you get a flare that breaks away from the solar surface, you can get gamma emissions from the sun. That indicates energies of millions of degrees. So the question is, well, why is this flare producing these gamma rays? So when you look at high energy X-rays or gamma rays that come from the sun, you see them mostly on the edges of the sun, towards the limb. You don't see them at the center. That's not because there's none produced at the center. That's because the light is coming to us from an angle. There's anisotropy there. What's happening is that when the flare is breaking through the surface, you have particles that are being propelled in the flare away from the solar body, and then there's particles that are moving across the solar surface that come and strike them. They're orthogonal to them, and when they strike them, that's when you get the energy release. So you get gamma rays because of the collision of these atoms, and this is true for all the stars. You have a thermal spectrum, but it's actually, that spectrum is not black. You can apply the equations of Planck and Wiens and Stefan to this. That's fine, you can do it, but you're only going to get an apparent temperature. You're not going to get a real temperature there. So it's a completely different way of looking at the problem than the astronomers have been looking at it. Like Eddington, for instance, was a well-known astronomer from Cambridge, and he's the father of the modern gaseous model. He just treated the sun as an ideal gas. And what's interesting about Eddington is he actually wrote right in one of his books that if he was sitting, on the Earth covered with clouds and he couldn't see the sun, he could analyze it just mathematically. If you're going to do that, you're never going to notice that the sun has convection currents because you never looked at it.
We are back today with our third installment with Dr. Pierre-Marie Robitaille. And last time we were looking at Kirchhoff's law and black bodies and some issues that had cropped up in the theoretical interpretation of what a black body even is. And now we're going to talk about looking at the sun and trying to gain material information from light spectra about the sun.
And this is the material application of everything we've been talking about before,
That's
right?
I mean, yeah, it's the next step, right? So the fact that last time we talked about the fact that there's a problem in Kirchhoff's law of thermal emission, that not all objects can create black body radiation. It takes a lattice to do that. Plasmas can never do that. They give line spectra. And if you enclose a plasma, you can get some broadening of the spectrum, but it's never truly black. There's always lines on top of it, like in the sodium lamp, for instance. So anyhow, if you want a true black body spectrum or a thermal spectrum that appears to be Planckian in nature, you're going to have a lattice. And that's the argument that I've made and that we discussed in the last episode.
And to have a lattice is basically to say that it cannot be a gas or a plasma.
Right.
And the sort of the frame for this is that the conventional wisdom is that the sun has a black body spectrum.
Despite being a gas.
Right. The sun has the continuous spectrum of the sun, the white light that we see from the sun, that spectrum is very close to that of a black body, right? And
very, very close.
This has been known since the days of Langley. And the astronomers assumed that since they had a thermal spectrum, that obviously they can take a temperature from it. They made several steps. One of them was to take a temperature for the photosphere, which they set at around 5,800 Kelvin. And that was an error. I mean, Max Planck, I think I mentioned it last time, complained that you cannot take a temperature from the sun using black body methods. And actually, I brought, this time I found the section number. Last time I was struggling to find it, but it was section 101 in Planck's book, The Theory of Heat Radiation. And I thought we should just read it because the astronomers, interestingly, they just ignored what Planck had to say. But he made it very clear.
If I can just preface that with, I don't think Planck didn't believe that we could get thermal information from the sun. He was just saying that perhaps the black body model wasn't appropriate.
What he was saying Well, we'll read it and then we can discuss what he said. He said, now the apparent temperature of the sun is obviously nothing but the actual temperature of the solar rays, depending entirely on the nature of the rays, and hence a property of the rays and not a property of the sun itself. Therefore, it would be not only more convenient, but also more correct to apply this notation directly instead of speaking of a fictitious temperature of the sun, which can be made to have meaning only by the introduction of an assumption which does not hold in reality. So what is Planck talking about here? What assumption? So the first assumption that you have to make when you take a spectrum using Kirchhoff's law on a black body, the first assumption is it has to be contained in a rigid enclosure. Well, the sun is not contained in a rigid enclosure. That's the first thing. It has convection currents. So because it has convection currents, the energy that's contained in the lattice field is much, much lower than the true energy that's sitting at the photosphere. Now, I've argued this for almost 20 years now.
Why is that? Why does a convection current change the temperature?
Right, because you've got, so in a solid, when the lattice is vibrating, right, you can't have convection, right? All the atoms are restricted to their lattice points, right? So they're vibrating around that, and that is why in graphite you get an accurate temperature, because the energy is perfectly monitored. The lattice is perfectly monitored by the emission spectrum. But when you have a liquid, and this has been known for almost over 150 years, I mean, in the 1800s, people knew that liquids were bad thermal emitters. And for instance, and this we'll go back to when we talk about the oceans and the microwave background, that the oceans aren't black bodies at 300 Kelvin. That's not correct. And part of the reason is they do have convection currents, so some of their energy is lost in these convective modes. So the sun has convection currents, and because it does, the energy, if you look at the total energy distribution in the surface of the sun at the level of the photosphere, you have some of the energy is contained within the lattice and its vibrational degrees of freedom. And then you have some energy that's contained in convection. And then some of the energy could be contained in conduction, for instance. So you have three possible places, three possible pots where you could put the energy that's contained at the level of the photosphere. So the astronomers are saying, well, all the energy is manifested by the vibrational lattice. Well, no, they never talk about the vibrational lattice. They say all the energy is properly sampled by the emission spectrum, and that's given us a correct temperature. And that's false. You're getting an apparent temperature there, which is just sampling the vibrational lattice of the sun. I've said that the sun has a vibrational lattice, and that's what we're sampling. Now, obviously,
so can I just summarize what you said real quick, just to make sure that it's clear for everyone?
Yeah.
You're saying that you can definitely look at the sun and get some thermal emission information. You can get some idea of a temperature, but you can't apply the black body model to get that temperature.
So you get a temperature, and the question is that temperature real or is it apparent?
Yes.
Okay, so what you get is you're actually getting an apparent temperature, and that temperature does have meaning. It's associated with the amount of energy that's in the vibrational lattice. That's what I'm saying. That 5800 Kelvin is not a measure of the true energy at the level of the photosphere. It's a measure of that energy that's in the vibrational lattice.
Got it.
The lattice
so you
is
think
vibrating.
that it's much hotter, probably. Is that what you're saying?
What I'm saying is that the photosphere has enormous energies, and so you get gamma rays. For instance, if you get a flare that breaks away from the solar surface, you can get gamma emissions from the sun, and that indicates energies of millions of degrees. So why? Mm-hmm. So the question is, well, why is this flare producing these gamma rays? So and the gamma rays are anisotropic. In other words, when they're produced at the surface of the sun during a flare, if at very high energies, like more than 10 mega electron volts, if you look at those flares, they're anisotropic. In other words, they're not distributed, they're not radiating, evenly like a nice, beam coming out in all directions from the surface. No, they have anisotropy. They're emitting preferentially in one direction, like as a little cone, but nothing coming normal from the sun. So when you look at high energy X-rays or gamma rays that come from the sun, you see them mostly on the edges of the sun, towards the limb. You don't see them at the center. And that's not because there's none produced at the center. That's because the light is coming to us from an angle. There's anisotropy there. And what the astronomers are trying to say, well, look, we have mirrors that are coming. Basically, we have energy that's coming from the corona, and it's striking the surface, and then there's a mirror plane there somehow, and the energy is reflected, and it's giving us gamma rays. And to me, this is just reaching for an argument. What's happening is...
So you think there's a lot more energy in this system, in the sun, on the surface of the sun, than is simply manifest by this black body reading?
Right. There's a lot more energy there. And what happens is that when the flare is breaking through the surface, molecules are coming, atoms are coming and striking the energy that's... So you have particles that are being propelled in the flare away from the solar body. And then there's particles that are moving across the solar surface that come and strike them. They're orthogonal to them, and when they strike them, that's when you get the energy release. So you get gamma rays because of the collision of these atoms together. And the collisions are telling us now we've got energies in the gamma rays.
So you see evidence that the surface of the sun is much more energetic than the temperature reading would reveal. And you think this all sort of comes down to a mistaken interpretation of treating the sun as a true black body, when in actuality, it's sort of a hodgepodge of different things.
Right. It's got convection currents, so you can't just treat it as a black body. And this is true for all the stars. You have a thermal spectrum, but it's actually, that spectrum is not black. It's not... You can apply the equations of Planck and Wiens and Stefan to this. That's fine. You can do it. But you're only going to get an apparent temperature. You're not going to get a real temperature there.
Got it.
And that apparent temperature is associated with the amount of energy in the lattice field. So it's a completely different way of looking at the problem than the astronomers have been looking at it, which, for them it's been 130 years thinking that they properly understood the temperature of the solar surface. And of course, Planck in his writing here on section 101, he warns them that it's a fictitious temperature. You're not going to get a real temperature here. So why was Planck saying that? Well, obviously he realized that there were convection currents. Now, if you look at the astronomers, like Eddington, for instance, was a well-known astronomer from Cambridge, and he's the father of the modern gaseous model. His book, The Interior Constitution of the Stars, in 1926, kind of set the stage for what came later. Now, there were contributions before that, of course, by Lane and others, and but his book, he just treated the sun as an ideal gas and thought, well, this was an appropriate treatment. And what's interesting about Eddington is he actually wrote in one of his books that if he was sitting, on the earth covered with clouds and he couldn't see the sun, he could analyze it just mathematically, just by looking at the mass of the sun. If he knew the mass of the sun and the equations for the gases, he could analyze the sun. Well, of course, if you're going to do that, you're never going to notice that the sun has convection currents because you never looked at it. And that's
seems like a classic mistaking of the map for the territory kind of situation.
Yeah, he just pretended like the math was a proper treatment of this problem, and it's not. You have to determine first, what is the phase of the sun? Is it really a gas? Now, people have given me a hard time, because I talk about the gaseous sun, or the sun is a gaseous plasma, and they think I don't understand the phases of matter. I'm not the one that first said that the sun is a gas. So I want to show people, I just want to discuss this point, because, here's a book by Kippenhahn. This is the classic textbook. Now, this is an old edition on stellar structure and evolution. And this is the book that you would take in graduate school to study solar theory, and I actually audited the course, as I mentioned before, with Pinsonneau, and this was the book that Marc used. And if you look at this book, you just look at the titles, it's got titles like the thermodynamic quantities of a pure hydrogen gas, the degenerate electron gas, the complete degenerate electron gas. And if you go to the polytropes, like here, polytropic gaseous spheres. So, these people were treating the stars as polytropes, and they called them gaseous spheres. Well, why? Because they thought that they were ideal gases, right? Isothermal spheres of an ideal gas. So I'm not the one who called the stars gases. I mean, this is coming from the astronomers. Now, I specify that they're actually gaseous plasmas. I'm very particular about that, and I call the sun a gaseous plasma, and people don't like that. And they say, well, it's like you're mixing phases like liquid solids. Well, people don't realize that liquid solids do exist. They're called liquid crystals. And if you look at like classic books on liquid metals, this is a classic text on liquid metals, and you'll see that in classic books, both in this one and in this one on liquid state physics, okay, in these books, you'll learn about the one component plasma and as a reference liquid. So what's the one component plasma? Well, that's really what I'm saying we have in the sun, right? We have a lattice, a hydrogen lattice, it's hexagonal planar, and the electrons are flowing inside the conduction bands that are created in this lattice arrangement, and that's
which is kind of like a slurry, right? Plasma. There's like little chunks of lattice moving about. The lattice is sort of a slurry, right? Like you see little sheets of lattice moving past one another, like a liquid almost.
Yeah, it could be. Well, I have some requirements for the sun because you have a thermal spectrum. The lattice has to be. There has to be a real lattice there. It cannot just be a soup of flowing atoms.
And the reason for this
structure. Now,
and the reason for this, hold on. I really want to clarify this point about the structure and gases and lattices and the spectrum. So if I understand this correctly, the reason that you argue that there has to be a true lattice is because there's a continuous there's a continuous emission spectrum of wavelengths in the visible light and into UV and infrared, which gives the appearance of the sun.
Right.
And the
gases never do that.
And the reason that a gas can't do that is because of the way that the gases vibrate. Is that correct?
Well, gases don't have a lattice, right? They have at most, like let's say a simple gas, like a helium gas. Helium has no bonds, so there's no lattice, definitely.
And without a lattice, you wouldn't have other vibrational modes, is what you're saying.
Helium has no vibrational modes. But let's say hydrogen. Well, the hydrogen molecule would have a vibrational mode.
But it's a single vibrational wavelength that gives you a very distinct bright band.
And it gives you line spectra, right?
And what happens inside of a lattice is that you have this vibration, but it can basically spread out through the lattice, which gives you a diffuse. It basically has all of the various vibrations that are possible.
Right. Now let's go back to hydrogen. Now I should say that hydrogen doesn't have a dipole moment, so it doesn't have vibrational lines. But let's say you take hydrogen chloride, for instance, it has a dipole moment, and so it'll give you vibrational rotational lines. There are many lines, and they're discrete lines where you have a mode, a vibrational rotational mode, and then no emission, and then another vibrational rotational mode right next to it. So it's basically that has a dipole moment, you have vibrational rotational modes, and you don't have that in hydrogen.
And it's light that's interspersed with darkness, basically, and that's not something that you see in the sun, because in the sun you see a continuous line of wavelengths. Right.
In the sun you have a continuous spectrum, and that's why, you have to have a lattice to do that, and you touched upon it, that the lattice introduces all the vibrational modes. There are many, many vibrational modes in that lattice, and that's giving rise to all the frequencies that are continuous, right? Mm-hmm. So that's why it requires a lattice, and a gas just can't do that. And the astronomers have tried to say, well, if we have an optically thick gas and all that, but this is just nonsense. You can make it as thick as you want. It doesn't matter. The modes just aren't there.
Well, so my question is this. If you have a sun that's made up of lots and lots of different atoms that are all emitting at various spectrum, could you have a gas that looks like a black body?
Well, that's what the astronomers try to do. They try
I see.
So what they try to do is they say there's something called the stellar opacity problem or the solar opacity problem. And people spent millions and millions of dollars, I kid you not, over the years, trying to understand how a gaseous object like the sun could produce the thermal spectrum. And
So this is a recognized problem, is what you're saying.
It's a recognized problem. So the first thing that they bring in is the negative hydrogen ion. Okay, they say, well, this is the major contributor to the solar spectrum, and the idea was brought by Wilt, and then it was echoed by Chandrasekhar. They thought that, okay, well, we're going to build a sun using the negative hydrogen ion, and then, which is a very implausible scenario in the first place, because this is a very unstable ion, right? And
But how do they argue that gives continuous band?
Yeah, they argue that will give you the continuous spectrum. Most of the continuous spectrum will come from the negative hydrogen ion.
Why?
And then, in addition to that,
Hold on. Why would the
why
negative
would-
hydrogen ion offer a continuous spectrum? Do you know?
well, they have two electrons, and one of the electrons is captured, and then they can argue that Brandstrom radiation. I mean, but the problem is you're still going to get a sharp cutoff. And
Basically, they say that that extra electron can have any energy state that they want, so it can generate any kind of light that they want.
Yeah, they try to say, well, we can put that energy, that electron, we can move it and get this continuous spectrum. But the problem is that it just can't. And even with the negative hydrogen ion, the solar physicists introduce many other processes, a great amount of processes in order to create their thermal spectrum. So what they do is they take all these processes that have nothing to do with thermal radiation, and they put them all together in a soup, and they say, oh, now we get a thermal spectrum. Spectroscopy doesn't work that way. So in graphite, there's only one possibility. You got vibration of carbon atoms within a lattice structure. That's it. And that gives us the thermal spectrum from graphite. So the sun has to use a mechanism that's close to that. It can't. The astronomers aren't allowed to just say, okay, now we're going to take a sum of 1,000 processes, and from these 1,000 processes, we're going to get a thermal spectrum. It doesn't work that way. Whatever happens in graphite has to happen on the sun, and that's why you have to have a lattice. And I'll stand firm on that, and eventually I will be proven right. I mean, this idea that you can solve the opacity problem of the sun by taking the sum of many processes it's an outdated idea that just needs to be kicked out of science at this point.
It sounds a lot like adding epicycles.
Exactly. And the problem is that the astronomers are so invested in the gaseous model of the sun, that the sun is a gaseous plasma. Everything hinges on that in astronomy, right? The Big Bang hinges on it because it's the reverse mathematics of the sun. And the Big Bang hinges on it. The black holes hinge on it. If the sun is condensed matter, all this stuff goes away. So it's really calling for, hey, we need a re-examination of modern astronomy.
Why does the sun being condensed matter change all of those other things?
Because now you're going to require, once you require that a lattice produces the thermal spectrum, right? Only objects, if you have a thermal spectrum, it came from a lattice somewhere. And the Big Bang never had a lattice, so it's over. I mean, that signature, we'll talk about the microwave background in another episode, but that signature did not come from the Big Bang. It's impossible. They don't have a lattice to produce it. And the same is true, unfortunately, for Dr. Hawking. He doesn't get to have black holes and Hawking radiation because he's claiming that, well, we get Hawking radiation because we're going to get black body radiation, very low temperature black body radiation from a black hole. Well, you can't, because a black hole doesn't have lattice structure. So you'll never get a thermal spectrum from a black hole. So this brings in tons of problems in astronomy, in fundamental astronomy. So there's a lot
fundamental
of
changes sort of in the way that we look at light coming from the heavens. Like, what does it mean? Like interpreting what this color of light actually means, what this spectra of light actually means.
Right.
Can I ask you this? Is black body theory, let's call it theory, it's sort of the black body equations, the maths, are those the only way of analyzing temperature from light?
That's not the only way. That's a difficult question, a little bit difficult question because
if there's a better way, like why, I'm wondering why these scientists are limiting themselves to this sort of model that they know probably isn't the right one to be using.
Well, no, they believe that they can fit their thermal spectra, like Penzias and Wilson, or they had a thermal spectrum. They fitted it using the equation of thermal radiation, Planck's equation, and Stephan's and Wien's, and you can fit these equations onto this data, and you get a spectrum. You get a spectral temperature. Okay.
Right.
And that's typically the way that it's done. Now, the question about temperature, does it have to have a thermal spectrum? That's more complicated than that. For instance, in the microwave background, there's cyanogen lines in distant stars, and those lines are reporting a temperature of about 3 Kelvin in distant stars. So the question is, well, is the microwave background there? Because we got it cyanogen lines, and we take the ratio of these lines, and we know the temperature. So anyhow, there are other ways of getting temperatures by ratios of lines and so on. But
I guess what I'm trying to ask is that if the shape of that curve fit applies to other thermal processes, like liquid thermal processes, but you wouldn't use a black body math to interpret it, despite the fact that the curve fit is approximately Planckian.
Well, if the curve fits approximately Planckian, you'll get an apparent temperature. The temperature, you'll calculate a temperature, it just won't be real.
But there's some oddities about the temperature of the sun as it's reported, right? Because you have, don't they think that there's a zone of millions of degrees Kelvin that's right above the surface that you just
So the
corona,
it's a good point. I mean, they tell us that the surface of the sun is at 5,800 Kelvin, and then the corona is at millions of degrees, right? If you go one solar radius above the solar photosphere, in that region, you have millions of degrees temperatures according to them. And what I tell them is, no, you don't. Actually, if you look at the continuous spectrum of the corona, because the corona does give a continuous spectrum, the K corona, and they tell us that the K corona is just reflecting. So you have relativistic electrons in the corona. So they invent, we have relativistic electrons, and these scatter the light from the photosphere, and they give us the K coronal spectrum. But the problem is that if you look at the K coronal spectrum, it actually reddens as you get farther away from the photosphere. That it moves to the red, so that means it's demonstrating that it's cooling. And I'm saying that the reason you have a K coronal spectrum, the continuous spectrum of the corona, is because you have condensed matter there. The sun is ejecting material all the time in its corona, and you have condensed matter in it. And that condensed matter has a lattice, and it's going to give you a continuous spectrum, which is cooling as you get away from the photosphere. So now the temperatures that they get come from line emission. So they don't come from the continuous spectrum of the corona. They come from line emission in the corona. So you get like iron 25 lines in the corona, So they say, well, gosh, if we have iron 25 here, we need temperatures of millions of degrees, because on Earth, to get the iron 25, we've created an equivalent temperature of millions of degrees. Okay.
I see. So those aren't black body readings at all.
No, those aren't black body readings. Those are coming from line emission of ionized ions. And because they're ionized and they're highly ionized, they say, well, in order to get that much ionization, we need these high temperatures. And so the corona is at millions of degrees. And I actually completely disagree. It has nothing to do with it. What's happening is that in the corona, you have some condensed matter, and it's electron starved. So you have some metallic hydrogen that's been expelled from the photosphere, and it's sparsely distributed in the corona. You see it in streamers and so on. And what happens is that you have atoms free atoms that interact with this condensed matter, and when it does, the condensed matter just rips the electrons away from it, right? It has a higher electron affinity, so it steals all the electron from iron and then releases an iron which has a single electron left, and that electron emits light, and they say, oh wow, we have whatever, iron 25 or whatever the case may be, and because of that, we know that we have millions of degrees. No, you don't. You have electron affinity. So you have condensed matter, and you've taken a gas and you've interacted with condensed matter, and the condensed matter has had a high electron affinity and just pulled all the electrons away. It's not more complicated than that. It has nothing to do with temperature.
Can you explain condensed matter a little bit?
Okay, so condensed matter, what I'm saying is if something is condensed matter, it's either in the liquid or solid phase, right? It has a lattice. So condensed matter is like salt, right? Salt has a lattice of sodium and chlorine for those who took freshman chemistry. Mm-hmm. So you have a lattice structure. Well, in condensed matter, you have a lattice. Now, in solids, the lattice is rigid, okay? And in liquids, the lattice can be fleeting. So the bonds of a liquid, they can break and reform and so on. Okay, so in a liquid you can have fleeting behavior, but in the sun, the sun appears liquid. If you look at it, it appears liquid, right? You have convection currents, and we know that it's going to have a lattice, but that lattice has to be somewhat liquid-like because there's convection currents. But you have to be careful here because it could still be, on the dimensions of the sun, I mean, this could be quite solid in behavior. It could be an extended lattice, which is not very fleeting, but its modulus of elasticity is quite high because, the dimensions of the sun are so great that, even if I took, that you take a rail bar, a railroad tie, or a railroad steel for the rail, the track, and, it does bend. I mean, it's not completely rigid. And on the dimensions of the sun, you can have a solid that, it looks like it's bending quite a bit, but it's actually got a pretty rigid lattice in there. So what I say is that at the microscopic level, we have a lattice. And macroscopically, it can still look like a liquid, but there is a microscopic lattice. That's in the 40 proofs paper. There's a footnote there where I clarify this point.
And so what you're saying is that the corona is mistaken to be much hotter than it actually is, right, due to the way that the condensed matter behaves with other atoms.
Is stealing the electrons away from free atoms, and when it strips those electrons away, the free atom looks bare. And so on Earth, the way you get bare atoms like that is you get them from heating them, right? You strip the electrons away, and so when they see these highly ionized species, they think, well, gosh, the temperature up there has to be enormous. So
so they're like missing a bunch of photochemistry.
Have come up with all kinds of ways to heat the corona, right? Because they have their solar photosphere at 5800, and then they have to put millions of degrees into the corona. So they come up with all kinds of schemes to heat the corona, And every few years there's a new popular scheme of this is how the corona is now heated. We understand it so well, and there are dozens of heating. Ziering called it a zoo of processes, that they come up with to try to heat the corona. And
okay, so another question.
They have to do that is they're just barking up the wrong tree. These ions are not hot.
What is the mechanism by which condensed matter is able to strip electrons from something like iron? Because it's condensed hydrogen.
I think it's just photochemistry is what he's saying.
Yeah, what's happening is that you have, it's just like if you have two rods in solution, one's positive and one's negative, and the positive rod wants the electrons, is going to take it, it's going to harvest electrons from the solution, take them out of the solution. So it's the same thing. If you have something that's highly positive, so you have, let's say you have metallic hydrogen in the corona. Well, as you go higher and higher above the photosphere, right, well, you start losing neutrality. The thing gets more and more ionized. The electrons want to flow towards the sun, right? So it gets more and more, it has a higher and higher electron affinity, more and more positive as you go up in elevation. So that's why these atoms, when they come and hit it, they get stripped of their electrons. Now, it's a quite interesting process, and I think people are not thinking. They went down this route for 100 years, and they never thought about what would be the implication of putting condensed matter in the corona, and if that condensed matter has a high electron affinity. Nobody has ever considered that. And once you do, then you realize, oh yeah, of course, if you've got condensed matter, you're going to have electron affinity, right? You see it in lightning on Earth, right? Lightning produces X-ray emission in the atmosphere, and of course, lightning is the transfer of electrons between two condensed plates, right? The Earth and the clouds. You have condensed matter up in the clouds, right? You have water. So you have two condensed plates, and there's a potential difference, and then the electrons are just pulled, because of the electron affinity that wants to equalize this charge difference. So the same.
Do you think that people get the temperature estimates of lightning incorrect by the same line of thought?
Well, you can have X-rays in lightning. Nobody is saying that the lightning's at millions of degrees, right? The atmosphere of the Earth is not at millions of degrees, but lightning can produce X-rays. And that's been seen, it's known. So, and that's because what do you have? You have the transfer of electron between two plates of condensed matter. So you see it in volcanoes, right? Volcanoes have lightning. And what do you have? You have charge transfer. And because you have condensed matter, and some of the condensed matter is electron starved, and wants those electrons, it's going to pull it away. So people.
These seem like very understandable mistakes by some measure. Like if you have this one way on Earth of looking at temperature in plasmas, and you're like, well, just by the color we know it has to be this hot, then it seems like an easy mistake to make.
Well, there are mistakes made because if you get the color, in condensed matter you get the color, and that color is telling you something about the temperature, right? And
unless the color is coming from
you're going to get different colors.
Unless the color is coming from this other electrochemical process, the light, isn't a thermal process.
Yeah, so lightning is not really a thermal process, right? The electrons are flowing from one plate to another, and it's like an arc discharge, right? So,
So, go ahead.
Well, I just wanted to say, I guess we kind of got into the topic a little bit fast about.
Yeah, let's take a step back at this time, and we can circle back to open questions about solar structure and how you came to this. But first, let's tell the story of your entry into this, because we've covered.
So well, last time I think we talked about the New York Times article, and when that was my first statement that the sun is condensed matter, and then how do you what we never talked about is how do you move from that, So I knew from talking to my friends that, look, there's no way that I'll be able to publish this in the regular literature. So what do I do? So I took out the ad in the Times, and then after that I started presenting abstracts at the American Physical Society, and I had made a point of, I'm going to try to go to as many local meetings as I can, because the American Physical Society has meetings in the Southwest, North, New England, Ohio section. There's a whole bunch of sections. There's a Texas section. So I'd go and present talks, So one time I drove all the way from Columbus to Texas to give a 10-minute talk, and I drove back. So, so I started presenting abstracts. But then the next thing that happened was, what do you do after the abstracts? So then I decided to put something in a patent journal. There's this patent journal, Research Disclosure. Now, this is really paid to publish. This is for people who want to say something because they want to get a U.S. patent. And so in here, I actually took out, presented evidence for the sun being condensed matter, and it's, the solar photosphere evidence for condensed matter. So I put that in Research Disclosures. And so that was in 2006. And then after that, the next thing was really, it's amazing how things fall into your lap. So there were a couple of Russian physicists. They were well trained. They had trained at Moscow State, and Dmitry Rabunsky and Larissa Borisova, and they were both people that worked on general relativity, but they wanted to form a new physics journal, and they did that in 2005. And their basis for forming a journal was their declaration of academic freedom. And Dmitry has, you know, if you read, if you go to the journal, you'll see that that's what he cared about. You know, people have accused Progress in Physics of being a predatory journal. Well, it charged $10 a page to publish an article, so nobody's making any money here. So it was never a predatory journal. Dmitry and Larissa, they started the journal because they saw that there was suppression of ideas in science, that the archives started preventing even Nobel Prize winners from putting their papers in the public archives. And so that's the Cornell archives today, but back then it was at Los Alamos, I believe. So, you know, so people were trying to control who gets to say what.
What was the
And
rationale
Dmitry
for
didn't want
that?
And so he came out with Progress in Physics, and
Hold on, before we go on to Progress in Physics, what was the rationale for preventing people from publishing their papers in the archives?
Well, they still do it today, right? So if you I can't send something to the archives because they have certain people that you can't put anything there. Now, interestingly, the archives have permitted joke papers against me. They're not real scientific papers, but they're sitting in the scientific archives. And so they permit this kind of childish, petty behavior in the archives, and that's fine. I mean, it doesn't bother me one way or the other. I mean,
and it's
have
surely
the archives.
political? You see this as like political Machiavellianism, or what's going on?
Yeah, I don't know what it is. But now there's an alternative archives today called VIXRA. So archive is arxiv.org, I think. And then there's somebody in England started another archive which is called VIXRA, the opposite of archives. And they permit anybody to post anything. Now, people will say, well, gosh, not everything should be posted. Well, who's to decide, right?
Right.
We're big boys. People can read and decide for themselves. But so Dmitry ended up forming Progress in Physics, and he said, you know, all scientists shall have the right to present their scientific research results in whole or in part at relevant scientific conferences, and to publish the same in printed scientific journals, electronic archives, and other media. And that was from his Declaration of Academic Freedom. And so what happened is that I started publishing papers in Progress in Physics, and then in 2011, this special issue of Progress in Physics came out asking the question, you know, the sun, liquid or gaseous? And this entire issue is filled with papers that I either wrote or had translated because they were important papers in early astronomy. So that became the next venue, Progress in Physics, and I used it because, you know, these people, Dmitry and Larissa, I mean, they had been well trained as physicists. I mean, Larissa was a woman, and she had trained with probably the top cosmologists in the Soviet Union. So, I mean, she's not a pushover. I mean, so people who attack Progress in Physics, they attack them because they don't like what they read in Progress in Physics. But, you know, they're people that have, Halton Arp has published in Progress in Physics, the famous astronomer that we talked about in the previous episode.
The redshift guy.
Yeah, the redshift guy published in Progress in Physics. Hafley published in Progress in Physics, with the Hafley experiment, the Hafley-Keating experiment. That's a very famous experiment. Bo Leonard, who's a member of the Swedish Academy of Sciences, he publishes in Progress in Physics. And the reason he wanted to do it is that because he wanted to retain his copyright. So he decided, I'm not going to surrender copyright to journals anymore. I'm just going to put in Progress in Physics. I always retain my copyright, which is one of the things that Progress in Physics does. So people have all kinds of reasons why they publish there. Progress in Physics supports scientists from poor countries that would have trouble saying what they have to say in the big journals, and you know, they could afford the $10 a page for Progress in Physics, but they might not be able to afford the 120 or more dollars a page to put in a big physics journal. So anyhow, it's not a predatory journal. People don't like it because they can't control what went there. You know, Larissa and Dimitri and other editors read the papers and they decided, okay, this is going in. And people don't like that, but sometimes when you have a paradigm shift, you know, you have to be open to different vehicles to get your ideas out. If you don't do that, you'll never say what you want to say. So
well, there's a really big argument to be made against peer review. That's a mechanism on Earth that lots of scientists and theoreticians have problems with because of the fact that it prevents the turnover of ideas, since you're gatekeeping access to the mainstream publications. Right?
Well,
there's a team of experts that gets to decide if your paper goes or not.
I mean, I think in the normal progress of science, I mean, peer review has a definite place. I mean, when I was doing MRI, I mean, in the early days of MRI, sometimes the reviewers made some really good comments and improved the paper. So peer review can have a positive impact on papers. So that it plays it's a necessary step in most cases. But like when I did the AT, I mean, you know, there were 10 papers, as I talked before, that were published back to back in JCAT, the Journal of Computer Assisted Tomography. And the editor had specifically told me that he wanted to publish the papers and not prevent them from being published because of delays by peer review. He just wanted the 10 papers out. And part of that was he wanted the proper credit to be assigned for ultra-high field MRI. I mean, and after we had done 20 papers, the first 7 Tesla results appeared, you know. So there's no question that OSU and my group was first in ultra-high field MRI. That's undisputed. And but people,
I have a question about your perspective on the ultra-high field MRI. Do you think that those papers were more technological in nature or more scientific in nature?
they had both. So there were scientific questions, and then there were technical questions. So one of the first papers was design and assembly of an 8 Tesla scanner. Well, that's a technical paper. It talked about, you know, how you put the scanner together and what are all the parts and how did we do it. And so that's more technical. But then some of the papers were very cutting edge science. You know, the fact that there was no RF penetration problems, that there was no dielectric resonance problem, and the questions related to power. These are questions that were scientific in nature. And then, of course, there were the medical discoveries, right? That we saw structures in the head that we had never seen before at ultra-high field. So it was both, right? It was a technological achievement, and then it was a scientific achievement as well, you know. It brought up a lot of scientific questions, and people that had hesitated before to go to ultra-high field or to go to higher fields that said, well, 1.5 Tesla is about as well as we could do. But after the 8 Tesla images came out, you know, there was a huge push in the MRI community to go to higher fields. So 7 Tesla with their slightly larger bore became commonplace. And then it also pulled all the 3 Teslas forward. So there's no question that ultra-high field has advanced all of magnetic resonance, both in our understanding of it and technologically for the patient. I mean, things just got better because there were ultra-high field scanners.
I think what Quinn's trying to ask is if you had some sort of technological application of your gaseous sun critique, do you think you'd have a better chance in the peer-reviewed literature? Is that what you're saying?
Well, at some point, it'll slowly come into the peer-reviewed literature. I mean, I might not be the person that's putting it there. I mean, for me, the central thing was to get the ideas out. You know, life is limited. You don't get to live forever, so I'm not going to fight with a reviewer for 10 years to get one paper out. There are too many consequences to a liquid sun, and people just need to read the papers and think about it for themselves. If they disagree with me, that's fine. They can disagree. But the ideas, so, you know, I always say science is like seeing my wife, a beautiful woman, you know. Once she's in your mind, you can't take her out of your mind, right? And ideas in science are the same way. You know, people might object to the idea that the sun has a lattice initially or that the sun is a liquid. initially it's reactionary. They're opposed and they're angry and whatever, and how could he say this, and he's not an astronomer, whatever. It doesn't matter. They start thinking about, does the sun have a lattice? They can't help it. They'll go to bed at night, and even if they, I always say, people can argue with you one day, and then 5 years later, they'll privately say to themselves, you know, that guy was right. And that happens both in our personal interactions with people, you know, where maybe we made mistakes in interactions with someone, and we realize years later that, I really mishandled that. I wasn't right about that. And that happens also in science because we're human, right? So somebody could say no at one point. They say, no, it cannot be a liquid sun. You're completely wrong. And then slowly time passes and they start thinking about the evidence and it just becomes overwhelming. They say, oh my gosh, the sun does have a lattice. So
it seems like that's the only way that people change their minds.
Yeah, it'll come, but it doesn't matter if it happens in my lifetime. But what is important in my lifetime is that I put the ideas out there so people can consider them. Like when we were talking about the solar corona, for instance, you know, people have to think about the ideas. And then, like, for instance, in the chromosphere, I said, well, the chromosphere is a site of proton and hydrogen recapture, you know, that the sun is not just permitting its hydrogen just to leave. You know, it recaptures it in the chromosphere, and that's why we get emission lines in the chromosphere. And I've talked about that in papers on the chromosphere and why the emission lines occur. And I link the emission lines in the chromosphere to condensation reactions. And there's a very good scientist, Erdl. I think he won the Nobel Prize in chemistry, and he did a cluster reaction. We took two silver clusters. So I think they were silver 4 or something. And these clusters came together to form silver 8. And then what happens is that once they form a complex, they emit one atom of silver, which is excited, because the complex is in excited form at first, but it needs to relax. So how does it do that? It emits one atom of silver, and then that atom has the electron in excited state, and then that electron then emits a photon and relaxes. Now this has nothing to do with temperature, right? The reaction is done maybe at 10 Kelvin. It's done ultra cold for these two silver clusters to come together, and then you emit light. For the silver atom is emitting light. So this is what I'm saying. Analogous reactions occur in the sun. In the chromosphere of the sun, we have condensation reactions. And in early stars, in the Wolf-Rayet stars, what I'm saying is the reason that those stars have emission lines is because you're seeing condensation processes. The stars are being formed and you're getting condensation, and that's why you're getting emission.
So this has really informed also how you think about the birth of stars themselves.
Right. It's related to how I think about the birth of the stars because, so, you know, the gaseous model, it just says, well, this gas just magically compresses by the hands of God and gives us a gravitational collapse, which is a violation of thermodynamics. You cannot get gravitational collapse, and we could talk about that in a minute. But what happens, what I'm saying happens is that you have condensation reactions. So, but if you're going to condense something, you know, you have to get rid of the heat. So how do you do that? And Erdl's reaction shows that in silver, right? The two silver clusters come together, but now they're in an activated state. You got to get rid of that heat. So what do? You eject a silver atom, and the silver atom has an electron which is excited, and it goes back to the ground state and emits light. So what happens is that the fact that you're getting light emission in the chromosphere and in Wolf-Rayet stars, which are stars that don't really have an organized photosphere, that these stars, the early stars, are actually undergoing condensation reactions. So I think about it as a chemist, you know, and so I look at it differently. Now, if we look at how the astronomers look at the formation of a star, you know, they try to tell us that, well, this is going to be gravitationally collapsing. And this argument was made by Eddington, but the problem is, and then not just Eddington, even before him, Lane looked at, in the 1870s, Homer Lane published one of the first papers looking at the collapse of a gaseous mass, and you know, he came up with Lane, he didn't realize it, but he came up with something called today Lane's law, which is that the temperature is inversely proportional to the radius. So what happens is as the star collapses, the temperature goes up and up, okay? And this is what is true today for the sun, you know, that if you look at Eddington's equation for temperature, it's inversely related to the radius of the star. So the temperature, it's got Lane's law built into it. So as the sun ages and the radius gets smaller, and it loses material, well, okay, the temperature goes up. It's just nonsense. In the gaseous model, the stars can't cool until you reach degeneracy, and Chandrasekhar then try to solve this problem. But if I just look at gaseous stars before degeneracy and what Eddington did, the problem is that he's got a temperature equation, which is equal to the gravitational constant, the mass of the star, the mass of the proton, and then divide by 5 times the Boltzmann's constant times the radius. So he's got this simple equation, and it looks all great, except that the temperature in that equation is not intensive, right? So in thermodynamics, there's a rule that temperature must always be intensive. And you know, no matter where you are inside an object, you can put a thermometer and you can measure the temperature at that point, right? And that's fundamental to the zeroth law. All temperatures are intensive.
Well, it seems like the main problem is that this gaseous model of star formation requires that the object do work on itself.
Right, and I've talked about that the sun has to do work on itself. So
which
you
is
have
impossible.
An object that does work on itself, increases its own temperature and decreases its own entropy. It's just nonsense. It just cannot happen this way, and nobody has ever criticized it before I came along. You cannot have a non-intensive temperature. So
I feel like if this was an action movie, Eddington would be the evil supervillain.
No, well, I don't think he was actually a Quaker, probably a nice guy. I mean, I don't know much about Eddington. I mean, he had a lot of arguments with genes, but I mean, I don't know how he was as a person. But
he keeps coming up on the wrong side of our discussions.
Unfortunately, he does, because he was a proponent of the gaseous sun, and he made mathematics that endowed to the stars a negative heat capacity. So not only did he make them gases, but he said, well, these gases have negative heat capacity. So what is heat capacity? You know, you put heat in, you put energy into an object, its temperature goes up, and how much heat does it take for that temperature to rise? That's heat capacity. And heat capacity for gases is positive, okay? So Eddington, so the question I ask all the solar astronomers, they want to argue with me, answer this question. They're telling us that the heat capacity of stars is negative. Okay, how massive does a gas have to get before its heat capacity changes from positive, which is what we know happens in the laboratory, to negative for a star? How massive does it have to get before the heat capacity goes negative? They'll never answer that question because it's unanswerable for them. So the problem is you cannot have a gas that has a negative heat capacity, and that's what's built into the gaseous theories of the stars. And so, you know, people have attacked me on thermodynamics. I said, well, they have to get up early because I did study it and I'm careful, and you know, you cannot have a negative heat capacity for a gas.
Why is that?
Have negative heat capacities in certain microstates and individual phase transitions. You can, under extremely specialized circumstances, get negative heat capacities. But
what is the mechanism by which you can't have? Yeah, what's the mechanism by which you can't have negative heat capacity? Well, so they're saying that it gets big enough.
I mean, you cannot. Gases don't have negative heat capacity. You put heat into. You put energy into a gas, its temperature goes up. You take energy out of the gas, its temperature comes down. But what Eddington is saying is, you take energy out of a star and its temperature goes up. It's wrong. And so this comes from his mathematics. So and there's a whole bunch of things. I mean, we can go down to degeneracy, but I don't think it's necessary, you know?
But so you started to formulate these ideas, and you, after the special issue in Progress in Physics, you decided that it was necessary to get your ideas out to the community in a pretty radical way.
Oh,
what
yeah.
did you do?
Yeah, so what I did was, so after the special issue came out, the first thing I did was in 2007, I wrote a paper on the WMAP satellite. And I had told you about my friend John Wilkins in physics. And I told John, I says, I'm going to email every physicist in the world. There's about 70,000. And I'm going to tell them about the paper. Now, John says, well, I guess a short email is okay. And you know, it was, you know, there's a list. I mean, there's a list. You could find a list of all the physics departments in the world by countries. And then myself and my children sat down and we sent the same email to 70,000 people in 2007.
That's amazing.
About the WMAP satellite. And then after that, when the
Which is a cosmic microwave background radiation experiment?
yeah, it was a satellite that was related to the microwave background. And
How many people
analyzed the
replied?
images in there and said, you know, these images have no scientific meaning. So
How many people replied? So you sent 70,000 emails. What was your reply rate?
Well, it was interesting. I mean, of course, you got some people that were reactionary and they were upset and they wrote you nasty grams, and other people read the paper and thanked you for it. And most people were just silent. But I got nasty grams. I mean, it's okay. People don't realize, you know, you have to use the method of your time. So when Raman,
Yeah, sure.
when Raman discovered Raman spectroscopy, right? What did he do? He told his once the paper was published, he said he got his secretary. I read this years ago, and I think it's accurate that it was Raman who did this. He got his secretary to physically mail the paper all over the world. And a couple of Russians got it, and they had been working on the same experiment, but there fell into their hands Raman's paper, and it established that Raman had done it first. So Raman used the method of his time. He used physical mail to mail the paper. And I decided, look, I'm going to use the method of my time. I'm going to send emails. And people thought, oh, he's spamming the world. No, I'm not. I'm not asking for a dime from you guys. You don't want to read the paper, don't read it. But when I did it for the 2013 paper on the 40 proofs that the sun was condensed matter, again, we emailed 70,000 physicists around the world. And one of them that received it was Neil Ashcroft at Cornell, and Neil started corresponding with me because he was fascinated with the 40 proofs paper. So not everybody was, people try to paint, you know, like you'll see on the internet, oh, he emailed scientists and whatever, as if that makes me a terrible human being that I decided to disseminate my work. So remember, in science, there are two rules. You have to say it, and people must know you said it. So when I took out the ad in the Times, that was one way that I got to say it, and people got to know I said it. And then, of course, the emails then reemphasize that I said it, and, you know, people know I said it, and whether they like it or not, I mean, this is not a popularity contest. It's about getting an idea out, and that I'm not looking for 1 million supporters here. I'm looking for 10 or so, a few scientists that are young and will start thinking about it. That's the goal. It's not, you know, it takes just a pinprick to sink the Titanic. So it doesn't take, you know, a bunch of supporters that publicly get on up in public and say, oh, Robitaille's right. It doesn't really matter. I mean, you just need a few people that are quietly starting to consider it. That's it. And so that's why I went with those methods, you know. And then the other thing is about credit. You know, people always ask me about credit, you know. And I've been told, well, when the physicists change it and the sun becomes condensed matter, they'll just do it such that, you know, you don't really get the credit for it. They'll do it such a way that somebody else made some important.
They'll probably act like they always meant that.
Yeah, they always saw it and they always thought about it and whatever. And I remind people about, you know, Gay-Lussac and Charles' law. So there's a law in chemistry called Charles's law, and it was published in 1802 by Gay-Lussac. Now, Gay-Lussac, he didn't do the experiment. He just knew that Charles had done it, and Charles never published a thing on it. But he was so honest, he knew that Charles had done it, so he published Charles's law. So today it's known as Charles's law because Gay-Lussac was honest. And that's what's required in science, right? And so Galileo was the same thing. I mean, there was a guy, Di Castelli, he contributed to the projection of sunspots on a screen, you know, and Galileo used this. And he freely acknowledged Di Castelli's contribution, even though Di Castelli never wrote anything. So in science, there is a standard, and the standard is not that you published it in my journal or whatever. It's that you said it and people know you said it. And that's what's required in human honesty, right? So you say it and people know you said it, and we should be honest about who did what, and that's it. And,
I love that.
It's very gentlemanly.
That's how I look at it.
Yeah.
So anyhow, there's an interesting thing about, when you publish something, you also get, there's a reactionary force against you, right? People say, well, gosh, how could this guy say this? And he's not an astronomer, and they come up with all these reasons of, no, we're not allowed to think because we didn't get the right, approval from them to think. And science doesn't work that way. Discoveries come from all facets of science, and people will look at something, they see something a different way than you do. And this reminds me of what Galileo said, that the enemies of novelty are infinite in number. and that's always true, that at first you're going to get lots of resistance, and the enemies of novelty are infinite in number. You just have to tolerate them and to some extent forgive them. It's normal. They've been trained a certain way, and you just have to have some mercy for them, and just don't take it too personally.
Mm-hmm.
Yeah, it's almost like, how could it go any other way? Those reactionary forces can actually be stabilizing to some extent, that they sort of police the garbage most of the time, but they also work against progress in the same effort.
Right. They don't realize they're working against progress. They're trying to protect what is established science, and that's the duty of a scientist too. You do have to protect established science. So there's a fine line, right? You have to be able to be open to new ideas, but you have to be able to defend established science. So the problem with reviewing my work, for instance, here Dr. Robitaille is saying, Kirchhoff's law is invalid. Well, that's very hard for people to digest because they're scientists. So there's a law of physics, and it's called Kirchhoff's law of thermal emission, and it's got to be right because it's a law of physics. So, but like all the other laws, it has to be correct. And most people can't imagine that there's a problem in Kirchhoff's law. But for me, remember, at first I thought Kirchhoff's law was right, and it took me years of study to recognize that, there is a problem here. And, so in the first few years, I think from 99 till about 2002, I was thinking Kirchhoff's law was right. And then, by 2003, I could see there was a problem, and then I kept studying after that 2003 paper where I said that there was a problem with Kirchhoff's law of thermal emission. I kept studying Kirchhoff's law and then produced papers in 2009 and in the teens on Kirchhoff's law and why it's not correct. So for me, it involved years of study, and I understand why Kirchhoff's law is not right. So most physicists or most scientists cannot be expected to do that. They have their own work, and they don't have the luxury of spending years to go make sure, is that law that I use every day, is it correct? And so I don't.
And they have to assume that it is, because it's just going to drive everything to a halt if you have to question every assumption at every turn.
Exactly.
And this is exactly what you said about the job of the scientist, to maintain the status quo on one hand and challenge it on the other.
Right.
Because if you question too much, you'll end up just spinning your wheels. You'll never be able to make any kind of progress if you just have to go through and reassess fundamental assumptions at every single stage. What kind of life is that?
And so that's why you have to be, if you're wanting to enter this realm of, I want to bring a paradigm shift to science, you have to have some tolerance for people being upset. Don't get mad at people and whatever. It's a normal thing. They're upset, and you have some mercy for them. To me, it's kind of like playing chess. But my dad used to play chess with me as a child. I was never very good, but compared to my father, I mean, I'm okay, but I was never like my dad. But it's kind of like playing chess, right? If you play and you know that this person's checkmate, you could know it's several moves ahead that they're checkmate, it's over. Well, don't ridicule them. They sat down with you at the game and they were polite, and you have some mercy. There's a beautiful movie, In Search of Bobby Fischer, where this little boy is a child prodigy, and it's a true story. And and you see the human side of him, that he doesn't want to hurt his opponent, And so for me, I mean, what's the point? I mean, whatever the sun is, I mean, who cares? I mean, if you can't be nice to people, I mean, does it really matter? I mean, so you have to have some mercy and respect other people that are scientists. Now, that doesn't mean that you can't hold your ground. I'll hold my ground and I'll defend myself, but there's a proper way of doing it. So I'm very conscious of that, not to be, even people who hate me, or some people on YouTube, I mean, they make comments, they want my death or hoping for my death. And that's taking it a little far, I think. I mean, it's just science. You got to relax a little bit.
Yeah.
So, well, it seems like you could make a shining example for many generations to come about how to behave in the midst of a paradigm shift.
Yeah. Well,
and I think that's really valuable what you're doing.
Yeah. I mean, I don't know that I'm a shining example, but I have a great wife, and she doesn't like me talking about her too much, but I just have married such a wonderful person, and she has such a sense of right and wrong and charity. I mean, she became a physician. We were married when we were 19, and she went on to become a physician. And she has such kindness for people, and you have to, because when you die, I mean, who's going to care about the sun? I mean, when I die, I'm going to care about my wife and the children, those that I love, my children and my grandchildren, right? And that's what life is about. The rest is, you try to advance humanity and steer them in the right direction. You also don't want people to waste resources on ideas that are just, they're done. So you have to push, try to get them to adopt something that will be better. And
that seems like it's at the heart of this for you.
Pardon?
I said, this seems like this is at the heart of this research for you, where you want to help the world focus on a direction that will yield more progress, more promise, more discoveries.
I care about the big problems, and what I mean by that is that we spend a lot of resources supporting astronomy, and sometimes I really question it. I mean, it's not that I'm anti-science. I just think that there are real problems that they also require funding, and they don't require, that we make all these claims about the universe, and we spend a lot of money putting up satellites and stuff like that, and I'm all for looking at satellites, but you have to temper it, right? Wealth is something that you have to respect, and there are real problems that could be simply solved with small resources. So when we spend billions of dollars looking for aliens, like right now, I mean, people are starting to, this is a justification. I mean, whether I find them or not, I mean, they'll find us. If they're there, they'll you guys found me. So
exactly.
I really don't think that this is a proper investment of science to have something like the Park Radio Telescope be involved, which is in Australia, be involved in the search for extraterrestrial life. I think there are people dying on this planet who could be fed with minimal efforts. And so what are the real problems? Well, let's desalinate water, and, let's try to get better fertilizers, and, try to harness energy in a pure way. I mean, these are the real
try to
problems.
learn how to treat one another with more kindness. It's like you said, I mean, this is all about the human project. Science is about advancing the human project. And if you can't do it with decency, you're undermining the same very project that you're aspiring to bolster.
Yeah. And so we have to think about, when I became the director of MRI at OSU, back in those days, the only 1.5 Tesla MRI in the city was at OSU. So we'd see, 10-year-olds with brain tumors come in to our scanner, and I'd see the scans, and, you knew that this is basically a death sentence, this kind of tumor in a 10-year-old. And I mean, there are real problems and practical things that we should solve, And that, for instance, I was talking to Steve the other day because I had an episode with sepsis, and Steve told me that's the #1 killer in the world. And why should it be? And so we have to decide where we're putting these resources. And the astronomers are always making great claims about all kinds of things. They make enormous claims, and okay, now we're chasing black holes in astronomy, and I think this is all science that's going to go away someday. We're going to spend billions of dollars on it. It's not going to advance human knowledge, and but it justifies our radio telescopes. Now we can put them all together, and now we have a large telescope array, and we can see farther and see objects that really. Does anybody really care about this? I mean, if I've got a 10-year-old dying of a brain tumor, do I really care if I've seen these objects? Are they even real? I mean, so much is data processing and so on. I really have, coming from a medical background of having worked in MR and seeing the suffering of humanity, I have to question astronomy, even though I spent a lot of my life trying to steer them on a proper course and reviewing their work and so on, but and it did pull me away from MRI. It's hard.
That's a really hard question, right? Just allocation of resources. What is the greatest good? These are enormous questions.
These are enormous questions, and the problem with peer review. One of the problems with peer review is, of course, the peers review their grants. I mean, astronomers review astronomy grants, and they award funding for these grants, right? And people who are doing biophysics, they'll review the biophysics grants and so on, and everybody's trying to protect their pie. I remember when emergency medicine was formed as a discipline. So, 40 years ago, when my wife was, I think she was in the second class of emergency medicine at OSU, but 40 years ago, emergency medicine was a new specialty. And I had worked with somebody, Dr. Angelos, who he became the chair. I think he's still the chair of emergency medicine at OSU. And he was working with sepsis. And he was very concerned about sepsis, and he would write NIH grants, and he couldn't get them funded. Well, of course, there was no emergency medicine study section, right? The study sections were cardiology, and there could be other study sections, but none was devoted to let's fund emergency medicine. So for the first guys, they could have been doing very important work, but there was no funding mechanism for them. Mm-hmm. So that's one thing about peer review that people don't realize, that you have peers, and the peers, they want to fund work in their discipline. Mm-hmm. And they're not too much thinking about, well, should there be more money spent in other disciplines? Condensed matter physics should get much, much more funding in my mind. Mm-hmm. Because in condensed matter physics, I mean, it's boring. People think it's boring. Everybody that goes into physics wants to go into astronomy. People don't say, well, I want to go into condensed matter physics. And this is a very, very important area of physics, because it's through new materials that we're going to harness energy better. And we need to understand materials much, much better. So I would put much more money in condensed matter physics. And in medicine, I'd put much more money in bacteriology. I remember telling my son, microbiology is going to be the science of the future. It's extremely important. And so it's an.
But these are less attractive disciplines because they don't allow people to think about. I mean, astronomy and cosmology are disciplines that literally tell people they'll find out about the beginning of the universe.
Such cosmic questions. They're like bigger than physical reality, even.
These are myths that humans have been obsessed with.
We try to make these questions so big, but sometimes the real problems that humans. I remember when we had I can't remember. It was the Horizon well in the Gulf of Mexico that was leaking oil for months and months and months. We couldn't go plug the well, So we're polluting all the Caribbean, and we had no means of plugging the well. Why? Because we never planned for it, right? And so humanity has to think about what's at home, our oceans, and preserving them. We don't have them. It's not good a situation. We digress too much, but we could go back to the sun a little bit. Sorry.
Well, I wonder if we shouldn't just put a pin in it for today, and then next time we can get into some of the more important consequences of your work on the sun, because you have an entire channel, which I might add is just incredibly deep, and
Sky Scholar.
It's in this very episodic format. You can watch these 10-minute videos. You could watch as many as you have time for, end on end, or one a day, but you could get all the details of Pierre-Marie's work on the sun there. And I don't even know if it's necessary for us to repeat a lot of that stuff, but it would be really cool to find out more about what this means for cosmology and astronomy in general.
The implications.
The implications.
Yeah, I think maybe next time we could talk about the microwave background and
Yes.
and the sun. I mean, it's welcome to break whenever you guys are ready. I mean,
Yeah, let's do that. So just to tease that, the basic idea, if I could just sort of paraphrase what I think you understand about it, is that you extend this lattice level thinking about emissions to suggest that there might be similar lattice-like emissions from our own oceans that give a apparent temperature which might be being confused for the CMB.
right, and that's what we can talk about that next time. That the water lattice is complex, and because it has the potential to produce this 3 Kelvin signature, which people will say, well, gosh, how can that be? You know, the oceans are sitting at 300 Kelvin. There's no way they produce a 3 Kelvin signature. But I think people will be surprised, and then when they start thinking about it, they'll see that, oh my gosh, we better be careful here. Water can emit at 3 Kelvin. So anyhow, we can talk about it next time. And I'm sorry if I digressed a little bit into the philosophy of science, but
No, that's our bread and butter, Dr. Robitaille. We really enjoy that. Thank you.
all right.
Yeah, I think we covered a lot of ground today. So let's jump right into the CMB next time.
All right. Well, thank you very much for hosting me again today.
Our
All right,
pleasure.
take care, Dr. Robitaille.
Bye-bye.
Bye.
Bye.